the GCoE-ACE. This is a center at IIT Dharwad. Yeah, over to you, Abhijit.
Uh, Thank you, Professor Bharat. Uh, the Global Center of Excellence in Affordable and Clean Energy, called GCoE-ACE, it was conceived in 2021 by IIT Dharwad and Selco Foundation as a means to drive technology development and deployment in the affordable and clean energy space, specifically for underserved sectors of the Indian society. The center's efforts span clean energy generation, storage, energy efficiency, economy, and end use optimization, and all the allied socio-economic challenges, particularly in peri-urban and rural regions. The center is supported by the PSA Office, Government of India, and CSR support from many companies, including Honeywell and Infineon. To foster inclusive technological innovation ecosystem in these areas, the center is looking for related problem statements and innovative solutions through an innovative challenge called Catalyze Tech. Problem statements may be from sectors spanning livelihood, agriculture, allied agricultural industries, resilient micro businesses, built environment, health, education, etc. A submission form for this catalyzed tech for problem statements and solutions is going to be made available in the chat box. I request you all to take a look and see if you can contribute some problems or solutions in this challenge. I now request Professor Tejas to introduce our speaker for today and begin the talk titled Power Engineering Education in the Age of Climate Crisis, a Holistic View. Over to you, Professor Tejas.
Thank you very much, Professor Abhijit. Professor Ned Mohan joined University of Minnesota in 1975, where he is currently the Oscar A. Scott Professor of Power Electronic Systems and Morse Alumni Distinguished Professor. Professor Mohan received his bachelor's from IIT Kharagpur in 1967. He has his PhD in electrical engineering and master's in nuclear engineering from University of Wisconsin-Madison. He has written 6 textbooks which have been translated into 9 different languages. His areas of research are in power electronics and he holds several patents. Professor Ned Mohan is a recipient of many awards. Professor Ned Mohan received the H.T. Morse Distinguished Teaching Award for Undergraduate Education from University of Minnesota. He has received IEEE PES Outstanding Educator Award, IEEE Undergraduate Teaching Award, Distinguished Alumnus Award from IIT Kharagpur, IEEE PES Ramkumar Family Renewable Energy Excellence Award, Innovative Program Award from ECE Department Heads Association, which consists of over 250 US universities, Distinguished Graduate Teaching Award from University of Minnesota, and IEEE Nari Hingorani Facts Award from IEEE PES, which is Power and Energy Society. He is a fellow of IEEE, a Regents Professor, and a member of National Academy of Engineering. He is the recipient of IEEE James H. Mulligan Educational Medal. I now request Professor Ned Mohan to share his experience and also to share the screen. We have a small request to the audience. We request the audience to post their questions in the Q&A box in the lower right side of the screen. I now request Professor Ned Mohan to share his thoughts. Thank you.
Okay. Well, good evening to all of you. And I certainly appreciate you inviting me to give this talk. And I'd like to congratulate you for establishing this center. And I wish you all the best as you go along with this center here. And I noticed that you have already started with a number of good, very pertinent talks. So I am very honored and pleased to be a part of it. And I'd like to share my thoughts on education. Okay, and I personally, I hope to meet all of you someday. And of course, I know Abhijit very well. He was with us for 3 years, and we have continued collaboration with him. So see if I can share my screen here. And it's always a challenge. So it says your entire screen. Okay, so here I share the button here, and it looks like it seems to be working. And I will go and see if you can see my slide. So can you see my slide here?
Yes, Professor, we can see it.
Okay, very good, very good. So this is the topic of my talk, and please ask questions, make comments as we go along. How do we provide power engineering education in this age of climate crisis? And what I propose is that we take a holistic view. So I have quite a few slides having to do with the seriousness of climate change, and that is still somewhat of a struggle here in the United States to convince people that climate is changing and changing very drastically, but not all of them agree that it's changing because of us. So I think that is, most parts of the world, that is not an issue. So here is a slide where just a month or so ago, it was 70 degrees warmer in eastern Antarctica, and then this ice shelf collapsed. So things are moving very fast. And we know that electricity is a basic human right. So 1.3 billion people, they may have some access to it, but not certainly reliable access to electricity. And 1 billion more would join us shortly. So I have lived in India in places where, for a while, at least at that time when I was growing up, I was born in 1946, so 1 year before independence. And there were places where there was no electricity where I lived. But at that time, it really didn't bother me because I did not know any better. But today, if electricity goes out for a short time, we begin to get very upset, so to speak. So we know that electricity is important, and it shows here this image at night that large parts of the world have no electricity here. So this slide, I am sure you have seen from IPCC, that as we speak, we are emitting something like 51 gigatons per year of greenhouse gases, 51 gigaton. And if you're going to follow this 1.5 degree centigrade pathway, as has been agreed upon in these climate summits, then we actually not just cut down on greenhouse gas emissions, but even we need to extract some of it which has been emitted. So that's a huge challenge. Okay, so you may have seen this book by Bill Gates. It came out actually this year, and he talks about different sectors and their greenhouse gases emissions. So first is making things, which is like, our production of goods and so forth, 31%. Let me see what happened here. I need to, okay, now it shows up here. I'll make it work. So it's 31% here. And then electricity, 27%. Then agriculture, getting around, and then keeping warm and cool. But you see here that a lot of these things would need electricity as we go on. For example, getting around. If we go to EVs, well, this would go up, okay? I'm sorry, this will actually come down, okay? Emission would come down, but the usage would go up, and therefore this will go up here. Electricity would go up. So the bottom line is that we should use all of our energy in the form of electricity, and then we should produce that electricity using renewables. So there is nothing new there. And this slide here shows the seriousness of what has happened. This Gavin Schmidt, he's the director of a NASA institute, and he says that compared to pre-industrial age, the temperature today is like 1 degree centigrade higher. So he says, is 1 degree a big deal? What's the big deal about 1 degree? But it says that it only took 4 degrees centigrade in the other direction to cause the ice age. So he says that we have already gone up 1/4 of ice age in the other direction here. So he has different scenarios, and if we don't do anything, it will be extremely bad. Even if we have serious mitigation, there are certain parts of the world that will be 4 degrees centigrade higher than pre-industrial age, and that's the same as one ice age unit, and this is for year. His predictions are for 2100. Okay, so I don't have the picture on a worldwide basis. It's not easy to get that, but so it's more a US-centric view. How do we produce power by various fuels here? So let's see here that in 2022, gas was number one here, natural gas. Okay, something like 35%, and then coal over here, and then we had hydropower, pretty stable here, and then also nuclear here. And the renewables, they are growing. So renewables are shown in green, and they're like 16%. So our goal is to move towards 100% renewables to produce electricity. So if you're at 16% at the moment, that means we have a long way to go, Okay, so, and also this geopolitical situation, this war that is going on in Ukraine, all countries are trying to stop imports from Russia. Okay, how are they going to substitute that imports, right? So chances are that a lot of them would go to coal, okay, which is the worst. So that's a geopolitical situation, not only hurts in this sense, but also it has taken our eyes away from combating climate crisis, because we have another crisis that is with us. So it's really our responsibility, because most of the technical solutions, and I like to point out technical solutions, they are electrically oriented, and so all of us in ECE have something to contribute. And I would say not just ECE, but all disciplines of engineering and sciences, they have something to contribute. And the educational effort that we are undertaking is that all universities, and again, when I say all, they don't have to be just in the United States, but this material that we are developing should apply to other universities as they see fit. Every place has their own need, their own requirement. So one size does not fit all. We recognize that. So as they see fit, they can use this material, and then we should bring this message of climate change in high schools and middle schools. So we are starting with high schools, but some people say that no, you should really start with middle school. I say, yeah, sure, why not? Why not? Maybe even elementary school, maybe, get that message across even when children are in kindergarten, right? So we have to do all that we can do. Okay, and then every course could include some aspects of sustainability, and then we should take a holistic view. Okay, so that's a big theme of this talk, this presentation, that world is not compartmentalized. So I talk about different sections or sectors of power engineering, power electronics, power systems, electric machines and drives and controls. But, we should not leave out other disciplines like mechanical. So, we should be designing things which are coupled together, like we used to call mechatronics at one time, right? So here is really our opportunity that we can create a vibrant program emphasizing at each university, and we can enroll large undergraduates and graduates. So, unfortunately, the numbers of students interested in power is not going down at our university, which is really puzzling. And we are still scratching our head, because everybody has heard of computer science and how much money they can make, and machine learning and data sciences and artificial intelligence. All of those are important. All of those can provide very good jobs. No question about that. But a lot of these young people are very passionate about climate, okay? And so if they're passionate about climate, if we can relate to them that, look, just having passion about climate, and if you don't do anything, what good is it? What good is it? So you have to do something, and if you want to do something, come and study electrical engineering and power systems, and you will do something, and there are plenty of plenty of high-paying jobs, So when we look at labor statistics here, we see that there'll be a lot of demand as there's a lot of money allocated for clean energy, clean electricity, for electric vehicles, electric vehicle chargers. So there'll be a lot of jobs, and they pay, very good salaries. Okay, so that's the message that we need to convey to high school teachers so that they can then convey it to high school students. Okay, so that's the mindset we need to develop. So that's what I mean, that even for us at universities, we have a lot of research and development funding. Somehow this pen has stopped working. I don't know why. Anyway, and then so this research should be interdisciplinary, right? Involving other ECE focus areas and other departments such as ME. Okay, so that's, and then here's the opportunity in terms of funding in the United States after this 1.2 trillion infrastructure bill that was passed. Okay, so I'll have to investigate about this pen. Anyway, so today we know at least in the United States, so this is US-centric, these slides, the carbon emission by transportation sector has exceeded that of electric power sector. And this crossover happened in 2016. Okay, so electrifying transportation is a big challenge and big opportunity. And then also if you can make it autonomous, that'll be fantastic. So, along with electric vehicles, we need electric vehicle chargers, and this electricity better be coming from renewables. Otherwise, there are reports which say that these electric vehicles otherwise would produce even more pollution. Okay, and we don't want that, right? So that's a challenge. And then we had done some work in 1990s and about charging of these electric vehicles, but it was then, and now of course we have better technologies here. So the answer is, as I see it, that we should shift all our energy use to electricity. Energy, whatever form we are using at the moment, we should shift it to electricity, and we should generate it from renewables. And of course, conservation is always should be a goal. And let's see here. It begins right now. Conservation should be a goal, and we should always have sustainability in mind, so to speak. So, there's no debating this argument here, that science alone cannot stop global warming. Human attitudes must change. We must change the way we think, where we live, and what we use and what we don't use. Okay, so when I talk about this holistic view, where all these areas of power electronics and electric drives, and of course their control, they should be looked at in a holistic manner. So here are some examples. Basically how we generate electricity generation, how we transmit it, and the end use. Everything should be considered from this sustainability point of view. And the same thing about transportation, whether it's by vehicle, automobiles, or whether planes or trains. And then, of course, defense is a big consumer of energy. And, role of defense is not diminishing. It's actually going up under this current geopolitical situation. And then, of course, industrial competitiveness using automation, and then, here is a biomedical engineering. So wherever we use electricity, and we use it everywhere, right? So here's an example of a holistic system. Wind turbine, you have a generator here, electric drives, power electronics here, and then you have a transformer, you're connecting it to the power system. So it's really kind of a combination of all these things. And one of the things that I find here in many US universities, that electric machines and drives, they are given a second-rate status. second-class status. Okay, but we should not leave out electric machines and drives, because a large fraction of electricity is generated and consumed by rotating machines here. So if you can make some efficiency improvements, especially using power electronics, we can increase the efficiency and therefore reduce the usage of electricity. And transportation, of course, is all about rotating machines. We have rotating generators in wind plants, and also concentrated solar power, not so much in fashion, but also nuclear plants even, right? So if you go to carbon-free generation of electricity, I would say that nuclear is a very major contributors as time goes on. So I'd like to hear your opinion, what you think about nuclear, okay? And because I think, as I see it, renewables being variables, and we need this energy, electricity 24/7, and batteries are not there yet. A lot of research is going on for this extremely large-scale storage. So I think one way to generate carbon-free electricity is nuclear power. Okay, and hydro is also relatively carbon-free, but there's not much potential left in the world to use hydro, and that has a lot of consequences as well. Okay, so we need transmission, because these renewables are located far away from load centers. So look at in California, this San Francisco is over here, a lot of wind here is in Oregon and Washington, and then also solar in the Southwest. So there are long distances over here. So we need transmission, and some people say that in the United States, this transmission infrastructure should maybe double, maybe triple. Okay, so that's a huge challenge. And who would build it? Who would design it? Okay, so education is the first step, and people are talking about using an HVDC overlay here. So also we need storage, because this famous California duck curve, it shows that because of all the electricity generated on rooftop solar during the noon hours over here, the use of electricity that utilities have to provide dips. Okay, so it's at this level at noon hour, and when evening comes, solar is going down, and people are coming home and turning on their burners and TVs and all those things. So in early evening hour, this peak power need occurs on the utility generation. So there's a tremendous ramp here, 13,000 megawatts in 3 hours. Okay, so that takes wear and tear on generating equipment, and that's where it'd be nice to have storage, 3 or 4 hour storage. Okay, but that storage is needed even on a very long term. Okay, so right now, and goal here is storage of $100 per kilowatt hour. Okay, and so that's the goal. But even at this goal, it'll be extremely expensive to store electricity for, let's say, there's some weather event where sun disappears for a few days and wind is not blowing. So how do we store that kind of energy? Okay, so that's a big challenge, and so people are looking at different mechanisms. Here is a iron air storage battery that one of my students, she went to work for this company called Enphase in California, and they build these micro inverters. But she recently switched to this company that is making iron air storage batteries. And of course, she is not a chemist or chemical engineer, but batteries, as you know, require power electronics. So that will be her goal here. So the bottom line here is that our research should continue in renewables. So you see here, as the installed capacity goes up into the grid, its value, which is shown in blue, goes down. So you can see this value is coming down here, right? And crossover happens with cost at certain installed capacity. Well, our goal is to increase this penetration. So if you can reduce the cost shown in this new cost, so now the crossover happens at a higher installed capacity. So this technological innovation can allow us to, increase the penetration of renewables into the grid, and then there could be some systemic innovations which will always keep the value lower, the value higher than the cost. Okay, so that's the need for research, and then we see that enrollments in electrical engineering part is nationwide going down. Okay, not just in power, but in other areas of electrical engineering in the United States. What is growing is computer engineering, and of course, computer science is off the charts. It's growing extremely fast. Okay, so when you talk about electric power engineering, we are talking about power systems, power electronics, electric machines and drives, and control. So what we did at our university, and that is just at our university's university, other universities may have their own way of looking at it based on local needs. We felt that undergraduate degree is not for anybody to specialize. They should have some specific knowledge of one area, a little more than others, but their education should be broad-based. Okay, so thinking about that, we, of course, these core courses in green that all electrical engineers have to take, but then, if you are in so-called power, then we had just 3 undergraduate courses in their 4th year: electric power, electric drives, and power electronics that you see in yellow. So just making it 3 courses, they have chance to take other complementary courses, and these may be from other departments, like from mechanical engineering. Maybe they learn something about heat transfer, things like that, or in computer science. They take some course on programming. So, when they graduate, they have a broad-based education. And after that, they may want to find a job in particular sector, but they may not be able to. And if so, they have the knowledge, they have the background, and they can start from there. So that was the motivation here. So over the years, with funding from this Office of Naval Research, which is a branch of the Navy, we were able to get funds, and we have developed 19 courses. And when I say graduate, well, there's some undergraduate too here. And I'll show you the list of these courses. And they are developed by experts in their own fields, power systems from academia as well as from industry, okay, especially in machines and also in power electronics. So we have put all those courses on this CUSP website, and URL is given over here. And so these courses are free to anybody, to everybody from any part of the world. You don't need to be a member of any sort, okay? You just go and you can download these videos, actually. So when I say a course developed, it also has lectures that the faculty in those areas have given. I think in India, there's a program like that, MPTL, I think, or something like that. We can discuss it later. And also, we are developing these pipeline courses to teach in high schools. Okay, so climate crisis and implementing solutions, that has already been implemented in 5 local high schools here. And then also we have a course on sustainable electricity supply. So this will be a very good course for non-electrical engineers and actually electrical engineers to take. So, when, let's say you're a mechanical engineer and you're working in a field where you need some knowledge of electrical engineering, especially power, well, if you take this course, you would have that knowledge. So I think I've been talking to Abhijit about this. In fact, we have a contract with Wiley. This will be a very, very important course as I see in the future. Okay, so these are the list of courses that we have developed. So here I may add undergraduate uh, as well as graduate students here. So you can see quite a few in power electronics, electric machines and drives. And these courses are backed up by textbooks, and and the lectures are recorded by the authors of those textbooks. So we are just thinking, what do we do with all this material that is on this CUSP website? Just because it's there, it's not sure, it doesn't guarantee that it's being used. So we want to go further, and I like to discuss that with you. So these are the pipeline courses that I mentioned to you, and they don't require any prerequisite, not even physics in high school. They need to have taken whatever physics is needed. We teach it in this course here. So last one time I taught, I had 111 students, and a lot of them were from other colleges like nursing, business, okay, English, things like that, and 60% were female. So we have been holding workshops, and so I'll skip over these here. So over the years, we have been developing laboratories. So starting at almost 2005, we developed these laboratories for power electronics and electric drives, and they have been acquired by 109 U.S. universities. But you see, they are about 15 years old, and obviously they are breaking down, and the legacy components cannot be found. So we had to update these laboratories. So we were very fortunate that we were able to get some funding from ONR, and so we have developed this laboratory here, which is for electric drives, and this is for power electronics, and we are working on a microgrid for power systems here. And also this power system course that we will be teaching uses PSSE, which is a very popular program for utilities in 140 countries. And then instead of using MATLAB Simulink, which everybody does not have access to, we're using Python, which is free. Okay, so University of Minnesota started this company called Sciamble.com, and my postdoc, now my colleague, Siddharth Raju, he's the founder of this company, Sciamble.com, and so these labs are being acquired, all over the world. Okay, so what are the main characteristics of these labs? First of all, they have a real free simulation and real-time control platform. So one does not need MATLAB and Simulink. So he, from scratch, developed this platform. He's an amazing guy, amazing. So just by himself, he developed this. And then using this platform, he can control these laboratories, okay, hardware laboratories. And they're like $3,500 per lab setup. Okay, so that is still quite a bit of money, because let's say in a lab you want to have 5 setups, and so you're talking about close to $20,000, and that is not easy to come by. If I had to get $20,000, it'll be a big hurdle. How do I get it, right? But another characteristic of these labs is that they are remotely accessible. So you see that these laboratories are controlled by computers, and you can control the computer remotely, right? For example, using remote desktop. So it makes them accessible remotely. For example, when we had this COVID crisis in March of 2020, we were teaching this electric drives laboratory in person, okay? But overnight, our university was shut down. All the buildings were shut down. University was not shut down, but the buildings were shut down. We could not even enter the buildings. So we made them remotely accessible. So there was no disruption whatsoever. Okay. And then we have, of course, the manuals, which can be downloaded freely from CUSP, and then reference books for these. But they can be used in student projects and research. Okay, so this is what remote accessibility slide here, that if you're controlling it with a PC, this laboratory here, well, you can control it remotely over the internet over here. So that's one of the great advantages of these laboratories here. This is what the simulation platform looks like, very much like MATLAB Simulink, but we do not use MATLAB Simulink. And when you're simulating it, you may have the model of the machine, for example, and you just take away that model of the machine and substitute with the actual machine. Okay, so it's extremely seamless, and you get all the results back onto your own computer. Okay, so this is what these labs look like. This is the electric drives lab, and so there's a box here which has the inverter and the controller on it, and then these are the motor generator sets that come with it, and so it's complete and already accessible here. So these are the list of experiments that you can do in the basic drives lab, and you can do vector controlled control, which we could not do with the previous lab. Okay, but now we are able to do vector control. Okay, and this is the power electronics lab, which is based on wide bandgap devices. Actually, it also has silicon-based devices. So on one side are silicon-based devices, and the other side are this wide bandgap, gallium nitride devices. And this is also remotely accessible and is complete. So these are the list of experiments that we can do, which we never could do before. Okay, like soft switching and single phase DC to AC inverter and three-phase DC to AC inverter we could not do, and these are digitally controlled. So that's another thing, and that's what makes them remotely accessible. And also we have this general purpose controller, and a lot of our PhD students have actually three of them who recently graduated made use of these here. And then we are working on an advanced power electronics lab, which will demonstrate, all the different types of converters that may be used for interfacing renewables to the grid. Okay, so here you can see here that we have, of course, two-level inverter, then this neutral point clamped inverter, and using flying capacitors, and then active front end, and then modular multi-level converters, MMCs, and also we will go into matrix converters, and dual active bridge principle will demonstrate. So all these things could be demonstrated in this lab. So I have a very extremely smart graduate student who came up with this idea that there'll be one sort of a breadboard, a sort of a motherboard, and which will have a lot of these power supplies and so forth. And then you can plug in these daughter boards for each of the different converters that we wish to demonstrate or for students to experiment with. So this is coming along pretty good. And, it's not ready yet, but October of this year, that's not very far away. Okay, and then we are working on this 5-node microgrid. And so it'll be like a tabletop microgrid that students should be able to get it, not students, but the university can get this microgrid, let's say for under $3,000. So for $3,000, this 5-node microgrid. And then we just got a grant from ONR, new grant, starting actually on July 1st in a few days. And this is for a low-cost, scalable, again, this thing, okay, a low-cost, scalable tabletop microgrid. Okay, so emulator actually for shipboard power system. So our idea here is that we should be able to connect hundreds of interconnected nodes, okay, and emulate them, not simulate them, but emulate them in real time, and then do what if type of analysis. What happens if there's a fault at this point, and how is that how does it affect, and uh, how to mitigate those type of things. So that's just a new one starting here, and so here are the list of experiments. I'll not belabor the point there, but we can do a lot of these things here. And then we are writing a textbook, and which is actually due end of this month, which is what is that? We are in June 30th, and today is 29th, is it? So it's not going to happen. It will be delayed by a week or two, but I think it will be done within 15 days. So this textbook has, we use PSSE, okay, which is a Siemens software. Okay, and so Siemens software, it's used very widely with utilities. I don't know how much it's used in India, but in the US, it's used quite a bit. And it has the reputation of being not easy to use, because it has so many parameters you can put in. So it's very flexible. But if you can make it very specific to the problem that we would like students to solve, then this program is not that difficult. So that is really the challenge we have. And I teamed up with a former PhD student of ours who works for Electric Power Research Institute, Swaroop Gugilam. So Swaroop is using this program PSSE day in and day out for his job. So he's very familiar with it, and he's demonstrating how to use this program. And the bottom line is to relay the concepts, the fundamentals of power systems, using this 3-bus system that you see here. One is a slack bus, and one is a PV bus, and one is a PQ bus. So using these 3 buses in a simple example like this, we can cover all the things that we need to convey to students here. So, so how do we acquire these remotely accessible labs from SciEMBL? Well, assuming each setup costs around $4,000, if you acquire 5 stations, it'll cost $20,000. And then you can offer this lab in person. But if you acquire just one setup, I'll try again here. Okay, so it'll cost us $20,000. That's a lot of money. But one can acquire just one setup for $4,000 and then timeshare with other students over the internet. Okay, so students can fill out a timesheet, and they can log into whenever nobody else is using, and make use of this lab remotely. Okay, and the third option, which is very tantalizing, is that we set up these experiments somewhere, and for example at SciEMBL, this company itself, okay, and at SciEMBL, and we license it to any university, let's say for $500 per semester. So all your students can access it, again, by signing timesheets at just $500 for one semester. Or who knows, this number may go down as we get more users. Okay, so our goal is to make it as low cost as possible, and allow these experiments to be performed by students all over the world. So that's really the goal. So here is my last slide. which says that our responsibility here is to do whatever we can. There's only one planet. There's no planet B, as they say, right? So this is really my end slide. But what I'd like to ask you along this, let me just go back to this slide here. So we have all these courses, okay? So what we are dreaming here, Siddharth and I, that we create some kind of a cusp academy. And this cusp academy, let's say, is non-profit. So we teach these courses by, contacting some knowledgeable professors to teach, and we pay them. So in order to pay them, if somebody decides to get a certificate, we can get a certificate. We can give a certificate, right? So, certificates may cost a little bit of money. And so each course, let's say, carries 3 credits. And if you take 4 courses, you can get a certificate, let's say, in power electronics. And that these courses may cost, I don't know what number to use, probably, let's say, $300 per course. Okay, so for $1,000 or so, you can get a certificate, okay, from this CUSP Academy. And if this has some credentials because it has all these courses and it has all these labs, it may be worth something. So I've been talking to people in companies locally here that what if we do something like this? Would they value this certificate? They say, for us, the important thing is that our employees learn. They know what they are doing because they hire people who really do not have this kind of a background. They may be electrical engineers, but they have never taken a course in power electronics, for example. So they can take a very thorough course, as thorough as we teach here, right? And so I think, so that's really our next challenge, so to speak, if we can create this CUSP Academy, and also if we can have these labs accessible remotely over the internet for a very small license fee. So my friends, I said enough here. I'll stop and I'll see if you have any questions. Let me go.
Okay, thank you, Professor. We would now like to take some questions in the Q&A box. Sir, the first question is, we have built over years AC grid transmissions. Will DC, which is a micro and mini grid network, boost the renewable energy production and usage? And second question in this, are these DC grids reliable?
Well, DC grids have been in operation for quite a long time, okay? And they have shown their reliability very well. In fact, the power that is flowing on DC lines can be controlled. So they have proven their reliability and their usefulness for stability and things like that. So I think there will be a move towards DC because if you're going to have all these renewables which are remotely located, so you have to bring that power from those remote locations, and building new transmission lines are not easy. Okay, so there is a lot of emphasis. People studying it, nobody has done it actually, is repurposing AC lines into DC. Okay, so the thing is that lower voltage DC lines could be very beneficial for renewables to bring power to load centers, and a very large voltage and large power, in gigawatts. Those are thyristor based, line commutator converters. So those, of course, are there, but I think there'll be very few of them in very, very few places. Okay, mostly it will be, so-called VSC, voltage source converter systems using, switches like IGBTs or MOSFETs, they, so I think maybe voltages which are not as high as what you talk about with thyristors, right? So I think there's we should be looking at DC. So it's under study, I think, in many places.
Okay. Sir, the same question on this thing. How about DC microgrid? Is it feasible in Indian scenario?
Yeah, DC microgrid is a very good idea, I think, because when you, even here, we are considering DC microgrids, because AC microgrids, you have to convert everything. The batteries are DCs, photovoltaics are DC, right? And so when you have DC, you have to constantly, you have to keep inverting it, and you lose quite a bit of, some power anyway, and the cost is there. So DC microgrids are certainly very feasible, and I think a lot of people are looking at it. I personally do not know of any in the US. Most of the microgrids that I'm aware of are AC. But then, if you have a DC microgrid, you need to have interconnection with the main grid, and that could be AC, right? So certainly DC microgrid makes a lot of sense.
Sure, sir. Thank you, sir. Next question. Are there any smart transmission in projects HV, MV, LV to meet reliable and climate change challenge issues?
Yeah, I would say when you say smart solutions, we are talking about these so-called FACTS devices, like flexible AC transmission systems, FACTS. So the primarily, these STATCOMs, static compensators, static war compensators, STATCOMs. So one way to provide reactive power on a bus is to have switchable capacitors, right? So you use in steps. So they are in operation using thyristor switches, and also so-called TCR, which is thyristor-controlled reactors, which can provide reactive power. So you could have hybrid combination of TCR, thyristor-controlled reactor, and this so-called, what is it called, where you have switched capacitors, SVC or something like that. So you can control the reactive power at a bus to control the bus voltage. But then better solution, I would not say better, but an alternative solution, which is a lot more flexible, but also probably more expensive, is to have this static converter-based STATCOM, which can provide both the real and reactive power within its design ratings in a kind of a continuous manner. You can change from reactive to capacitive, and I should say inductive to capacitive, and but in any step that you want. So those are being used, and so those are the two. I don't know. There are some where you have the ability to connect capacitor in series with the transmission line to increase the power flow capability on the transmission line. But they are just one or two for demonstration. They are in use actually, but they were built more to demonstrate that it can be done. But I don't know of any which are under consideration. But STATCOM certainly are being used.
Sure, sir. Sure. Thank you, sir. Next question is connected to the pedagogy. We have a half semester core course for power system for regular BTech students. It consists of 21 classes as compared to 42 classes for a regular full semester course. Any suggestion on how we can give general overview of power systems in such a short time?
Yeah, that's that's an extremely good question, because not everybody needs to know about power systems which will require 40 lectures or 42 lectures, right? So what one needs to do is to take a look at the topics that we need to cover, which may be of importance to people who are just taking it in 21 lectures. Okay, so you may find out that certain topics like I don't know which one to leave out, but how generators operate in power systems, we can leave that out. Or you could leave out certain idea, like certainly, uh, you know, these are not core power systems people, so you can leave out probably transient stability in detail. You can just mention it. You can mention a lot of these things, but you don't need to go into detail. Same thing about power flow. I mean, these folks are not going to design power flow calculators, right? They're just going to use them. So just show them there's some popular program that is used in utilities and industries in India, for example, and show them how to use it and how to get the results and how these results complement the fundamentals, the concepts they're learning.
Sure, sir. So one last question. There's another question. I have seen departments in some Indian institutes named high voltage engineering, sometimes a branch from electrical engineering. However, these are not at many places, at least in India. Can power engineering be a separate graduate level course or a separate department?
Yeah, that's very a question for the context of place. How it should play out. So high voltage engineering we teach in very few places in the United States, and but we should teach it because we still obviously use high voltage, right? Where that should be located, that is not for me to say, but so that is one of the strengths of these courses that I mentioned. Uh, we have a course on high voltage technologies, and this was prepared by Professor Ravi Gurar. He is a graduate from IIT Bangalore, and he was teaching this material at Arizona State University. Now he's the head of the department at University of Alabama in Huntsville. So, but he had a lab, high voltage lab. So we should teach these courses because maybe in a way that it's not a full course at any one university, but there's a course that students from many universities and industries can take, because we need voltage insulation coordination in power systems. So somebody has to know about relaying, power system protection. And if you teach this course at one university, you may not get enough students, and you may not have some faculty expertise to teach it. So what I would say is that it requires kind of a collaborative effort in some sense.
Sure, sir. Sir, thank you. And one last question may be quite encompassing. What is the support anticipated from the policymaker to achieve this holistic view, sir?
So that is stop sharing at this point here.
Sure, sir.
So, yeah, policymakers. I don't know. I don't know how to answer that question. Okay, because I think at least what I see here, everybody has a very short-term view. Okay, the goals of universities are very short-term. Okay, and there is, as I see it, nobody is looking at the big picture. Okay, long-term picture, like going into high schools and middle schools and promoting this message to the young people to pursue these careers, right? Mm-hmm. And so that kind of mindset is not there. I cannot say about India for sure, but here I can be quite certain in telling you that it's not there. Okay, and so policymakers, I mean, they are, of course, elected. So we are a democracy, which you may say is a good thing. but also in democracy they have to be elected every 4 years. So that's also problem that their goal becomes somewhat short term. How to get elected?
Okay, sure.
So I better not say any more than that before getting into trouble. So I'll stop.
Sure, sir. Sure. Thank you very much, sir. Thank you very much for sharing your valuable experience. We would like to thank Professor Ned Mohan for accepting our invitation and sharing his
Thank you.
valuable experience on trees and Samvad. We would also take this opportunity to thank our audience for making it convenient to attend both trees and Samvad talk and for having an interactive session. Updates of trees and Samvad will be regularly be posted on our website, on our institute website. We request you to regularly check the institute website for the upcoming trees and Samvad talks. Thank you once again and good day. Thank you, sir.
Yeah.
Thank you very much.
Yeah, thank you. Thank you very much. Thank you for having me. And I really I really enjoyed it.
Thank you very much.
You folks made my day. So
Thank you.
I appreciate it. Thank you. Bye-bye. Bye-bye.
Thank you.
Thank you, sir.
Thank you very much. It's our
Bye.
pleasure, sir. Thank you very much, sir.
Bye.
Thanks. Bye, sir.